Okay, let's hope in future it will be considered by many. So, we begin new chapter, chapter 3, infinite series. Today's section is 15.1, series with non-negative coefficients. Non-negative terms. Series with non-negative terms. So I'll start with definition. The expression A1 plus A2 plus so on plus AN plus so on, or shortly AK, is called infinite series. AN is the sequence of terms of the series. So, and once again, that is just a notation, symbol. Nothing else is behind this notation. It's like for improper integrals. Firstly, I wrote symbol without any meaning. Now we discuss which meaning can be given to this infinite sum. This is not so trivial question, in fact. Maybe you know Zeno's paradox. Achilles and Tortoise. So, look, imagine there is Achilles somewhere, right? There is Tortoise somewhere. Achilles tries to reach Tortoise. So Zeno's paradox says he will not. Why? Imagine Achilles runs through this distance up to the current position of the tortoise, right? What will happen with tortoise? Into the same period, tortoise will go some distance. Then Achilles runs that distance, tortoise walks for a certain distance. And we continue. Never. Right? Obviously, this is a paradox, and definitely in reality it can be. He will achieve tortoise. Why this paradox? How we can explain it? In fact, that is an example. Look. So, Zeno's paradox says, okay, we have infinitely many terms, all of them are positive, hence it will be never sum up. Why? It can be summed up. So it means this infinite sum may have a meaning. And now, which meaning? So next notion, the sum of the series and we denote by the same symbol is the limit if it exists of the sequence of partial sums. Partial sums. What are partial sums? K from 1 to n, ak. So, by the definition, what is the meaning of this infinite series, sum of this infinite series? By definition, that is limit as n tends to infinity, sum k from 1 to n, ak. So, once again, you should distinguish between notation for this sum, right? And its value, right? We can write this expression even for the case when this limit doesn't exist, right? If it exists, then the value of this limit is equal to the sum. Like for improper integrals, once again. And, okay. If the sum of the series AK exists and is finite, then series converges. Otherwise, it is divergent. Diverges. So convergent, converges, is convergent. It is divergent, diverges. So any expression can be used. So once again, we can write infinite sum for arbitrary terms. Then we can talk about the meaning of this sum. And we understand the meaning in this sense. So we take partial sum. So roughly speaking, how we understand infinite sum? We forget about this rest remainder, right? Tail of the series, remainder. We call it partial sum, and if the sequence of partial sum has a finite limit, then our series is convergent and its sum is called the sum of our series. Okay. Now, in fact, that is long definition, right? So many terms are included, and also I'll use notation for partial sums, short notation, and so if I'll denote the sum of our series like that, then by definition that is S equals to limit Sm, shortly, right? These are short notations for those things. Okay. Now, what can we do with those objects? So, I'll start with some elementary properties. Elementary properties. In fact, the first property uses some new notation, but I don't want to make it as a separate definition. So, first, definition will be included inside. Linear combination of two series, two convergent series, converges. So what is it? For arbitrary alpha, beta real, what we have? If we have two series, k from 1 to infinity ak and k from 1 to infinity bk converge, if both converge, then the linear combination, that is such series alpha ak plus beta bk converges, and its sum equals to alpha sum of ak plus beta sum of bk. So, it means that roughly speaking, we can proceed with infinite sum in a similar way to finite sums. So, common multiplier may be taken outside sum, and we can rearrange summations. That is, in general, in fact, you should be more careful about generalizations of usual actions with real numbers, I mean commutativity and so on, if we have infinitely many terms. But concerning this particular case, namely linear combination, no problem. And you see, it's quite obvious, right? You should just substitute the definition with the help of partial sums, and that's all. So I'll not prove it. And second, the series k from 1 up to infinity ak converges if and only if this series k from, let's say, capital K up to infinity ak converges. Here, capital K is arbitrary. So it means that you can forget about arbitrary first terms of our series. So, from the point of view of convergence, any finite number of terms is not important. It seems a little bit strange, right? Arbitrary finite number of terms is not important for us. Arbitrary. Billions, trillions, doesn't matter. But once you fix this finite number, we don't care. From the point of view of convergence, first terms are not important. What is important is what happens at infinity, right? What is going on when we approach to infinity. So, concerning the proof, let me write partial sum. So, denote Sn as before partial sum for our series, Sn tilde partial sum for capital K plus, I start from K, so first n terms of our series. Now look what happens then. What is the relation between them? These are partial sums of our series. We observe that Sn equals to, let's say, S with number capital K plus n minus 1 equals to, that is, what is it? Sum K from 1 up to capital K plus n minus 1 ak. And what is it? It means I summarize the first K minus 1 terms, A1, so on, up to A capital K minus 1. And then I sum up all others, and that is precisely capital K minus 1 plus S n tilde. So you see that once the sequence of partial sums Sn converges, so Sn converges, if and only if S capital K plus n minus 1 converges. And since those numbers differ from partial sums for the second series by a certain fixed number. That is fixed number, right? So if and only if Sn tilde converges. And that is precisely what is written. Okay. And one more, let me emphasize. Look, the title of that section is series with non-negative terms. But up to now, I didn't put this restriction. So those elementary properties are valid for arbitrary series. And the first result also is valid for arbitrary series. Theorem 1. Theorem 1. If the series converges, then limit of the sequence of its terms is equal to 0. So that is called necessary condition. Necessary condition for convergence. Of series. Proof is very easy. Proof. So, what is the definition? So, if it converges, then there exists limit of the sequence of partial sums. Hence, there exists limit of shifted partial sums. And what they are. And you see, we know from limits of sequences that doesn't matter if you shift it, it's practically the same sequence, so same limit. And then look, what is Sn? But Sn equals to Sn minus 1 plus the very last term. So here we sum up first n terms, and in that we sum up first n minus 1 terms. So one term more in that sum. So you see, tends to some s, tends to the same s, right? Hence, what is about limit of an? So, limit of an equals to limit Sn minus Sn minus 1, and that is because both limits are equal. And that is only necessary condition, and once again, this result is valid for arbitrary series, so not only with non-negative. That is not is important for us. Now, the proof is not by induction. No induction here. We are talking about limits. No induction. Just we compare two limits of two sequences. One sequence, just our partial sums. Other sequence, so what is sequence of Sn minus 1? It's the same sequence, but we start from, so you see, here, first term is S1. For that sequence, first term is for n equals to 1, no sense. Sometimes we'll denote, so if we start S naught by definition, so if you sum up, how many terms you sum up? Nothing, right? If you start from 1, but there is a question. Roughly speaking, it means that somehow the last term of our sum is always 0 if our series converges. No. Why no? Because no last term. There is no last term. That's important. We have infinitely many terms. There is no last term. Once again, you see. Doesn't matter how many first, finitely many terms we forget about. Okay. So, now, from now on, for this section, I'll suppose that all terms are, maybe not from now on, sorry. Firstly, let me consider one example, example 1, which is, I guess, familiar for many of you. We'll consider the series of that form, k from 1 up to infinity, q power k. So, look, if q in modulus greater or equal than 1, then limit of q to the power n is not equal to 0, as we know, right? Hence, by Theorem One, the series, what happens with our series then? Cannot be convergent, right? Since the limit is not 0. Hence, it diverges. But what happens for q less than 1? We can write down what is about partial sums. So we start from q, okay, let it be from q, right? So q to the power n, right? What is it? That is q times 1 plus on plus q to the power n minus 1, or using elementary algebra, we understand that is equal to this expression, right? And limit of q to the power n equals to 0, hence what we'll obtain, the limit of Sn is equal to q over 1 minus q. So it means that our series, hence the series converges and its sum is equal to q over 1 minus q. So let me recall once again that is valid for q less than 1 in modulus. Okay. So that is called sum of infinite geometric progression, right? And I guess you are familiar with it. Yeah. Without general notion of series. Okay, from now on, we suppose that all terms of our series are non-negative. And Theorem 2, I'll call it Criterion of convergence of series with non-negative terms. If an is non-negative for all natural n, then the series converges if and only if the sequence of partial sums Sn equals to sum k from 1 up to n ak is bounded. Proof. Proof is very easy. What we should observe. So, I will recall the relation between partial sums. And now, what we deduce from those two. Look, Sn equals to Sn minus 1 plus an, and is non-negative. So what it means? It means Sn is greater or equal than Sn minus 1. Right? And what it means for all n. So the sequence Sn is non-decreasing. And what we know about monotone sequences? Monotone sequence always has a limit, either infinite or finite, right? And it is finite if and only if the sequence is bounded. Yeah. So, hence, limit is finite if and only if Sn is bounded. That gives our assertion, right? So we obtain what we want. Okay, now an easy consequence is comparison test, comparison theorem. Theorem 3, comparison theorem or test for series. If for all n great natural, we have such an equality, then first, convergence of larger series implies, okay, let me write here, okay, implies convergence of smaller. Second, divergence of smaller implies divergence of larger. So you see that the assertion is very, very similar to comparison theorem for improper integrals, right? Also, there were non-negative functions, and convergence for larger implies convergence for smaller, and divergence of smaller implies divergence for larger. Similar is here. Okay. Oh, okay, let's have a break. Okay. So, proof. Proof. We refer to Theorem 2. So, first, sum of bk converges. Then by Theorem 2, partial sums, those partial sums, form bounded sequence. So this sequence is bounded. What it means? Sum k from 1 to n, bk in particular, less or equal than some constant c. for all n. For all natural n. This inequality is valid for all natural n. But then we deduce that partial sums of our series from AK are bounded as well, right? And from these, so it means the sequence AK is bounded. Hence, again by Theorem 2, by Theorem 2, sum our series converges. And second part of, okay, I may refer just to logic, right? So suppose that is not true, right? So there exists convergent series BK with divergent series AK, but it contradicts the first part. So second part follows from the first by logic. Okay. Yeah. Next test. And look, I said this theorem resembles very much comparison theorem for improper integrals, right? Very similar. And in fact, next theorem is a direct indication about similarity. So, Theorem 4, let me call it Cauchy-Maclaurin integral test. Test for series. Sometimes names are not mentioned, so just integral test. So, if f of x is continuous, non-negative, monotone function, in fact, I don't need continuity, is non-negative monotone function on 1 infinity, then the series n from 1 to infinity, okay, k from 1 to infinity, f of k converges if and only if improper integral from 1 to infinity f of x dx converges. Proof. So our function is monotone. Since I know by necessary condition that convergence may happen only when limit f of k is 0, right? And non-negative function, if it has a limit 0 at infinity and it is monotone, then it should be monotone how? Non-increasing, right? Non-increasing, decreasing. So suppose f is non-increasing. In fact, otherwise, if it is non-decreasing, then it means that the limit can be 0 only for the case when it is identically 0, right? And this is not interesting case. Otherwise, limit is not 0, and if limit is not 0, then it is easy to prove both are divergent. Okay, so then what we know? Let me consider integral from n up to n plus 1 f of x dx. So, for all x from this interval, what I know, because of non-increasing, the function is monotone, then I have the following inequalities. So, f of n plus 1 less or equal f of x less or equal f of n, right? Largest value is in the left end and smallest at the right end of the interval. And using monotonicity of integrals, I may integrate it. Since the length of the interval is 1, so integration of upper and lower bounds gives same expressions. So this follows. Okay, then let us sum up those intervals, those inequalities. So I used k. Okay, let me change to k everywhere instead of n. K is not important. Okay, instead of n everywhere, let it be k. Okay, then let us sum up from 1 up to n. So sum k from 1 up to n f of k plus 1 less or equal sum k from 1 up to n integral from k up to k plus 1 f of x dx less or equal sum k from 1 up to n f of k. In fact, this inequality proves everything. Why? Because look, suppose our series f of n converges. Then by Theorem 2 says that partial sums form bounded sequences. Bounded sequence is bounded. Bounded means that all of them are less or equal than certain number c, right? So then what those two inequalities give us? Let me go that. Okay, so what follows? It follows that the sum in the middle, integral from k up to k plus 1 f of x dx, which is equal to, if you sum up, look, so you integrate firstly from 1 up to 2, then from 2 up to 3, and so on. If you add all of them, you obtain integral from 1 up to n plus 1 f of x dx. And this is less or equal to c, right? Now, look. Denote capital F of x, integral from 1 up to x, f of t dt, right? From non-negative, from, let's say, positivity of our function, we deduce that f of x is non-decreasing. Because if you enlarge x, then you add some interval to integration interval, right? And it means you integrate non-negative function. It means that you increase your values of your function f of x. So f of x is non-decreasing. And look, for arbitrary x, if we consider integer part of x plus 1, right, that is an integer number. Integer part is, so maximal integer number which is less or equal than our x, or sometimes it is denoted by that one, right? Yeah. No, I'm sorry. That I can use only that. Yeah. That is an integer number, right? Now what we can write? F of x is less or equal than f of integer part x plus 1, and that is less or equal than c, right? So we have non-decreasing function which is bounded, And once we have non-decreasing bounded function, hence there exists finite limit as x tends to plus infinity. Because every monotone function has a limit, finite or infinite, and it should be finite because of boundedness. And what it means? A limit of capital F. A limit of capital F is nothing else but this improper integral. By definition, what is improper integral? We vary upper limit. That is what we have here, right? So it means that the integral converges. Now look, so I deduced convergence of integral from convergence of series, right? Now go back. So if the integral converges, now suppose, let integral from 1 to infinity f of x dx be convergent. Then what happens? Once again, it means that capital F of x is bounded above. Why? Because once again, convergence of improper integrals means there exists a limit, right? Capital F is non-decreasing, and if there is a limit of non-decreasing function, then the function should be bounded. Above and below, in fact, but I want to use boundedness above. Okay, hence we can put in particular f of n, okay, let it be n plus 1 is bounded. This sequence is bounded. So if the function is bounded, then the sequence of values at arbitrary points is bounded. And what they are? Fn plus 1, f of n plus 1 is nothing else but that one. Is bounded. Oh, sorry, k from 1 up to n. Bounded. And then this left part of our main inequality, left part, implies together with it, so those two things imply together that the sequence k from 1 up to n f of k plus 1 is bounded. And that is what? In fact, the same for our, so what is it? F of 2 plus f of 3 plus so on plus f of n plus 1. You see, it differs from the sequence of partial sums just by one term. And from the main property from the very beginning, it doesn't matter if we forget about one term. So, because of non-negativity, we deduce that the series f of n converges. That's it. So here we use another half of our main double inequality. And so theorem is proved, and now an example how to use that theorem. So example. By the way, in principle, you see, I said that we should suppose the function is non-decreasing because otherwise limit is not zero and nothing good may happen. But look, in fact, if the function is non-increasing, then what will be different here? You should change them, right? And you can repeat again the same consideration. So it doesn't matter. So the assertion is still valid, although, of course, the only, I mean, if it is non-negative and non-decreasing, then the only case when some of them converges is when we have identically zero, nothing else. But, of course, it is still valid, right? Yeah. Okay, now example. Example 2. Consider such a series 1 over k to the power alpha. If we consider the function f of x equals to x to the power alpha, right? Then it is monotone. Is monotone on 1 infinity and non-negative, right? So we can apply our Theorem 4, right? So by Theorem 4, okay, not from here, sorry, from that one, right? Theorem 4 says that the series k from 1 to infinity 1 over k to the power alpha converges if and only if the integral from 1 to plus infinity dx x to the power minus alpha, right? Minus alpha here, yeah. X is that one. So dx over x to the power alpha converges. And now we know when this is true from an example from a section about proper integrals. That is true if and only if alpha greater than 1. So, you see, we obtain a scale of convergent and divergent series, right? 1 over k to the power alpha. If alpha greater than 1, it converges, otherwise diverges. By the way, very important case, alpha equals to 1. That is, okay, let me use n instead of k. Harmonic series is called harmonic series. And it is divergent. Diverges. So you see, that is good example which shows that Theorem One gives only necessary condition. Remember, if series converges, then the sequence of terms tends to 0, right? Here, sequence of terms 1 over n tends to 0, but series is divergent, right? Okay. And few words about, look, we have a lot of similarity between series and the proper integrals, right? Even the result like that, just replace summation by integration, and it is still valid. You may ask, oh, maybe everything is valid, analogs, I mean. But that is not true, even for necessary condition. So you remember that what we know, if the series converges, then limit of an is 0, right? You may ask, oh, maybe similar thing is true also for integrals. Maybe it's true also, right? Look, very similar. Not true. So be careful. You see, we have a lot of similar things, right? So it seems, oh, maybe it's the same. No, that is not true. It's possible to construct an example, even for non-negative functions. Okay, so now let's go to more standard, SPT. Series with non-negative terms. Okay. Let me give. So this was some general information about series with non-negative terms, right? Or maybe let me change the title. General information. General information. So this was because I'm not able to finish everything what I supposed to do. Okay, so now next section, 15.2. It will be short section. D'Alembert test. So, suppose an is positive for all natural n. First, if upper limit of such a sequence an plus 1 over an is equal to, let's say, p less than 1, then the series converges. Second assertion, if lower limit an plus 1 over an, which is equal to q, is greater than 1, then the series diverges. Proof. Proof. So, for the first, choose epsilon greater than 0 such that p plus epsilon less than 1 as well. So p is strictly less than 1, then we can enlarge it a little bit to still have a number which is less than 1. So the upper limit of an plus 1 over n is equal to p. Then by theorem about upper and lower limits, I know it was very complicated, but we know that for this epsilon there exists a number n such that for all natural n greater than n, we have an plus 1 over an is strictly less than p plus epsilon. Then what we can do, let me estimate an plus capital N. I can write it like that. There is an plus capital N, an plus n minus 1 times n plus n minus 1, n plus n minus 2, times so on, times okay, the last when we can write it down is when n plus 1. So n plus 2, an plus 1 times an plus 1. Okay? Look, so what I did, I inserted some numbers and both in numerator and denominator. But then look, each of those terms is strictly less than p plus epsilon. Because here it's valid for arbitrary little n greater than capital N. And that is greater than capital N, right? Always. So that is strictly less than, okay, how many? P plus epsilon power, how many we have? We start from n plus 1 and finish with n plus n minus 1. It means I have n minus 1 such terms, right? Times an plus 1. Now, look what it means. It means, and what is about the series n from 1 up to infinity, p plus epsilon power n minus 1. Since p plus epsilon less than 1, right? Then this series converges. Sum of infinite geometric progression. Example 1. Example 1, section 15.1. Right? And then by comparison theorem, we deduce that the series n from 1 up to infinity an plus n converges as well. and it gives convergence of our series of AN. So the first part is proved. Second part is proved analogously, very analogously, but here we need to use another part of the same theorem about upper and lower limits. So, second part, choose epsilon greater than 0 such that q minus epsilon is still greater than 1. Q is greater than 1, so we can choose q minus epsilon greater than 1. Then, lower limit of a sequence is equal to q, hence there exists natural n such that for all natural n greater than this capital N, we have an plus 1 over an greater than q minus epsilon. And then we proceed in an analogous way. An plus n equals to n plus n, n plus n minus 1, so on. An plus 2, n plus 1 times an plus 1. Now greater than q minus epsilon power n minus 1, an plus 1. And we know the series q minus epsilon power n minus 1 diverges for q minus epsilon greater than 1, right? Again by example 1. So altogether they imply that the series an plus capital N diverges. And it gives what we need. Corollary, very important corollary, which is called usually ratio test. Ratio test. If there exists such a limit, limit an plus 1 over an equals to L, then first, if L is less than 1, then the series of an converges. Second, if L is greater than 1, then the series diverges. How to prove this? Because if there is a limit, then both upper and lower limit coincide with each other, right? And we refer to both halves of our assertion. You may ask what happens for L equals to 1. Look at example, the last example of former section with sum 1 over k to the power alpha. In any case, an plus 1 over an tends to 1. But you see, series might be divergent or convergent. So you have no conclusion if L equals to 1. Okay, that's all for today.